morning, Doctor. So now I will present our OS final project report, the paging concept. Okay, so first, let us talk about the abstract. So this project is an implementation of a paging-based memory management system of an operating system, which take a real-life analogy of a post office to make the idea easier to comprehend. So another program in is C++ language, where user can enter logical address to emulate the memory access. So when the page required is not in memory, then there is the page fault and the system load the page with a first in, first out page replacement algorithm. In the case where the physical memory is full, the oldest page is removed to accommodate the new one. This simulation gives a clear picture of how logical address are resolved to physical address, how page tables are updated, and how paging eliminate external fragmentation and enhance memory utilization. So the project increased the knowledge of how the operating system handle memory with the paging and replacement policy in a real-world situation. Next, let's talk about the introduction. Memory management is a fundamental function of modern operating system, ensuring that multiple programs can run efficiently between limited physical memory. Paging is a widely adopted memory management technique that divides logical memory into fixed-size block called page and physical memory into frames of the same size. The operating system maintains a page table that makes each page to a physical frame, allowing the process to be loaded into non-contiguous memory space and eliminating external fragmentation. So to help users better understand how paging works, this project implement a visual and interactive simulator in C++ using the analogy of a post office. So in this analogy, logical address represent call box number, physical frame are mail shelf, and if a page is not in memory, it is considered still on the mail truck. So next, let's talk about the problem statement. As a software application become more complex and memory intensive, operating system must manage memory more efficiently to ensure stability and performance. Traditional contiguous memory allocation techniques suffer from external fragmentation, leading to wasted memory and slower execution. So paging solves this problem by dividing memory into uniform page and frame and allowing non-contiguous allocation. However, paging introduces its own set of challenges, including the overhead of maintaining page table and the need for efficient page replacement strategy. In system with limited physical memory, a method is needed to determine which page to evict when memory is full. So this project simulates such a situation and implement a free-for page replacement algorithm. So the goal is to help user understand about how logical address are translated, what happened during a page fault. So lastly, by simulating this in C++, we provide a clear and interactive way to explore the inner working of paging and its practical importance in OS memory management. Next, let's talk about the related work. So paging is one of the most fundamental memory management techniques studied in operating system. In the textbook operating system, three easy pieces by Apache Ducio and Apache Ducius. The author explained address translation, page table, and how hardware such as the memory management unit assists in efficient paging. So the book offers practical insight into how virtual memory and paging interact to allow for multitasking and memory protection. So G4G, a popular educational platform, provide visual explanation of paging mechanism and how logical page map to physical frame. Another article describes virtual memory, highlighting how only necessary pages are loaded into memory, reducing overall memory load and improving multitasking capability. So tutorial point are also offer use tutorial on single level, multi-level, and inverted paging technique, killing their advantage, quick off, and real-world use case. This results from the theoretical foundation that support this project, where the implemented C++ simulator demonstrate how this concept work in practice.
Hello, Dr. Farkhana. So now I'm going to continue with the methodology. So our project shows how paging works in the operating systems, and this is our project management flow. So the first one will be the concept understanding. We begin by studying the concept of paging, page faults, and the page replacement strategies, which is the first in, first out. And this helps us to understand how the operating systems manage the memory efficiently. And the second one is the analogy selection. To make the concept easier to understand, we use a post office analogy, which the logical address is the PO box number, and physical memory is same as the mail shifts, and the page fault is same as the mail still on track. And this helps us to turn the paging concept into something that is more relatable in our real life. Yeah, and the next one is the simulation planning. So we designed a simple and interactive memory simulation systems. The users can enter the logical address and see how the system checks if the page is already in the memory, and if it is not in the memory, a page fault occurs and the system loads the required page. If the memory is already full, the system will replace the oldest page using the first in first out method, and this flow reflects how actual operating systems will handle the paging and the memory limits. And next one will be the system implementation. We implement this simulation system in C++ language, which allowing the users to interact with the system and see how addresses are translated and how page faults and replacement happens. And the last one will be the review and reflection. So the simulation system was tested and reviewed to ensure it is clearly demonstrate how the paging concept works. And this helped us to understand the concept more clearly and show that using a real-life examples can make these technical topics become easier to learn. Okay, so that's all for the methodology.
Hello, Dr. Farkhana. My name is Lim Singrao, and now I'm going to present about the design and implementation of the simulation. First of all, we'll see the flowchart of the simulation. We will first initialize the page table and the physical memory, and we will display the current state of the page table and the physical frame. We will let user to choose to access the appeal box, and the user can enter the value. After that, we will calculate the page number and offset of the PO box, and we'll see if the PO box is already valid in the memory or not. If it is, we will calculate the physical address and we will display the physical address. If not, we will see if there is any free frame available. If yes, we will use up the free frame and we will update the page table. If not, we will carry out a first in, first out replacement by replacing the oldest page on the physical memory, and we will update the page table as well. So that's it for the simulation of the memory of the post office. And now we'll look at the code implementation of the simulation. We're using C++ for simulation. First, we will do configuration and set up the data structure. After that, we'll initialize the page table. So each page table is initialized as invalid and not assigned to any frame, simulating that no logical page is currently loaded in memory, which also means it will be empty in the post office memory initially. We have a function to print the page table and physical frame to display the system state. We also have an interactive simulation loop that allows the user to display the system state and let the user to input their choice and also to input the logical address. And we also have a function to translate logical to physical address, a function that handles page fault with first in first out replacement when the physical memory is full. Now we'll look into the interface and the execution of this program. So the program provides a console-based interface that simulates a memory management system using paging and first in first out page replacement. After launching, the user is greeted with an introduction to the memory post office simulator. From the main menu, the user can enter a logical address representing a PO box, exit the program, or exit the program. The system then converts the logical address into a page number and offset, checks whether the page is currently loaded in the memory or not. If a page fault occurs, the system loads the page into memory using the first in, first out algorithm to replace an existing page if necessary. Look into the output, and we're going to trace the output to show the concept of paging. First, we can access the PO Box 18. After we have run the program, it will display the current state of the page table and the physical memory. And the user can choose to access the PO Box or to exit. So this is the menu. And the user can enter 1. After that, the user can enter the PO Box logical address from 0 to 63, for example. And the user can access like any PO Box number, for example here 18. And it will show accessing PO Box 18, and it will calculate the page number and offset. So we're looking for page fault offset too. Okay, page fault occurs because initially there is an empty in the physical memory. Page fault is not in the memory, so we must retrieve it from the mail trap. And we can find free shelf on the physical memory. So we have found free shelf 0. So we're going to paste page fault into the shelf 0, which is the frame 0. This simulates a page fault, yeah? And the final physical address is calculated by frame number times page size plus offset. So after that, we will load the page fault into the frame 0. So this is the system state after the loading page. It show that the page fault is valid and mapped to frame 0. And the physical memory will show that frame 0 contains page fault. Okay, after accessing enough address to fill all shelves, meaning that the physical memory is fully occupied by the pages, and if the user now still wants to access a new PO box which is not loaded into the memory is full, so first in first out page replacement is used. So we're going to replace the oldest page in the frame, in the physical memory. So page 4 is the oldest, right? It will be removed from shelf 0. In page 6, for example, the new logical address will be now inserted into the same shelf 0. And here's the updated system state. You can see that the frame 0 will contain page 6 instead of page 4, and the page 6 will be in the frame 0. So we'll move on to the discussion of the output. The simulation will demonstrate how the concept of paging can be effectively applied to manage memory in an operating system, using the memory post office as an engaging analogy. Logical addresses are represented as PO box numbers, physical memories as mere shelves, and page faults as mere retrievals from a mere trap. So this design makes the complex mechanisms behind paging more intuitive. So paging has very efficient memory utilization, since the memory is divided into fixed size pages and only the necessary ones are loaded into physical memory, allowing logical memory to exceed physical size without external fragmentation. And address translation and page table management, and also page fault handling and replacement strategy are basic operation of the paging concept. Output behavior and educational impact. So this simulation has displayed page hits, faults, replacement, and address translations clearly, offering visualization of the paging concept.
Now I'm going to proceed the future work and conclusion. With software application becoming increasingly complex and memory intensive, the efficient memory management is a fundamental challenge for any modern operating system. The abstract nature of memory management technique can be a significant obstacle to understanding them. After setting on our topic, we discovered that using a real-world analogy like post office was crucial for making the concept of paging comprehensible. This project demonstrates how paging allows process to be loaded into non-contiguous memory, which is critical for multitasking and eliminating the wasted memory caused by external fragmentation. We also discovered that the implementation used the first in first out page replacement algorithm when a page fault occurs and all physical memory frames are full. In this scenario, the system evicts the oldest page to make the room for the new one. So while this approach is straightforward to implement, a key limitation is that FIFO is not always the most efficient strategy in real-world scenarios. A future enhancement could be to incorporate more advanced algorithms like this recently used to compare their performance. The advantage of our simulation is that it clearly visualizes how logical addresses are translated, what happens during a page fault, and how a replacement policy works, providing an interactive way to explore this mechanism. In conclusion, this project is advantageous for us to acquire extra knowledge about the memory management, especially the paging concept. The implementation of the memory post office simulator using the C++ programming allow us to see the step-by-step process of the address translation and page fault handling. Consequently, we are able to understand how modern operating system use paging to manage memory more efficiently and readability.